today I have an inverter. It is a 410 watt inverter. And it's not enough. So I have another inverter. This is an identical 410 watt inverter. It's also not enough. How to resolve this problem? Well, I have two inverters and I want to run something that takes more than 410 watts. What can I do about that? The first thing that a lot of people think to do is to take your two inverters and connect both of them up to your battery with whatever cables you have available so that they're both running. Great, you got 400 watts here and 400 watts here. Maybe I need to power something that's 700 watts. So you think, ha, I'm creative, I know how to solve this. You get an extension cord, you cut it apart, you put an extra end on here so they're both male, right? Plug one into this inverter. Oh yeah, this is smart. Plug the other end into this inverter, and now they're both connected together, right? You got them both in parallel, and you can just take your load, whatever it is, say this goes to your 700 watt appliance, and you plug it into here. And then you turn the inverters on. Yeah, don't do this. This doesn't work. You'll just end up destroying both inverters, and then you won't have anything at all. So what I'm going to do today is attempt to parallel these two inverters, and then we're going to test it out to see how well it actually works. Now what I should be doing is first benchmarking these inverters as is, but they are 410 watt inverters, so you got a pretty good idea of what they can actually power in real life. So I'm just going to go ahead and make the modifications, and then we'll test the inverters. After all, this whole thing might fail, and you'll just end up with a pile of smoke and broken parts. So I'm going to see if I can get these hooked together in parallel as they are not designed to do. And I don't think I've seen anyone else do this on YouTube yet. There may be other videos, I don't know, but I'm just going to make my own, and we'll see if this works out. The first thing to do is to disassemble and inspect your two inverters. They should be identical, ideally, for this to work well, but what do I know, right? I haven't done this before. This is the first time I've tried to do this. So this is the inside of the inverter, and I went over what this inverter looks like in a previous video, but I'll quick do another synopsis. Your input terminals are over here. The positive runs through a couple of fuses. In this case they are 20 amp fuses, and they go through here and they tie into these two input FETs. Now the two input FETs unfortunately are powered. Here's your input terminal for ground, and it goes through this tiny little bus bar over here to these two transistors. And to me that's not acceptable. This has to be able to carry 50 amps. This doesn't look like a 50 amp connection to me. So I'm going to take some solder and beef this up a little bit. That will help the output capacity somewhat. Otherwise it goes through these two transistors, through this solder and copper over here, which looks adequate, through the transformer to the output stage. Now the output stage is low current because it stepped the voltage up 10x at least, more like 15x actually, assuming it's 120 volt output, which is what this inverter is, through these output transistors. Now one thing that I noticed when inspecting this is that most inverters send the output current, output's over here, output current through some sort of current measuring device, and when the current's too high they trip and shut down. That protects the inverter from overcurrent conditions. However, on this one I cannot find any place where the current could be measured, either on the input or the output. This Schumacher 410 watt inverter is kind of unusual in that way. They have all this surface mount components on this inverter on this side, and over here they have surface mount components and a bunch of through-hole components. It's kind of a expensive construction really, and yet it doesn't seem to do a whole lot. So I don't think they really actually measure any sort of current on this board. There's no current sense resistors or any sort of place where they could do that. So I believe what they're actually doing is measuring voltage drop, and I'll explain how that works. So you have your input voltage here, runs through your cables, through the circuit board, through these two transistors. These are the input capacitors, through the transformer, through these diodes, stores in this cap, and now you have 150 volts or so stored in this cap. And from there, this bridge outputs the AC to your outlets. It just chops it and puts it into square wave out the outlets, just like any modified sine wave inverter. But I think what this inverter is doing to sense over current is just checking the output of this transformer. It's supposed to be at least 120 volts. If it's not at least 120 volts, then you can't get proper voltage out the outlet and it trips. So I think what they're doing is just doing overcurrent protection in two different ways. One, they just sense that this voltage is high enough, and this voltage either gets too low because your input voltage gets too low, or because the losses in these transistors and the transformer and the circuit board and wiring is too great. So that's one way it protects itself. However, the other way is fuses. Yeah, maybe they're external for a reason, huh? Most inverters have these internal. You can't see them. Here they're replaceable. And you might think, hey, that's great, I can replace them when they blow. But you know what? This is designed for them to blow. They will pop if you overload this inverter and you have good voltage. That's the whole point of these fuses being external. They cheaped out on you, and now it's on to you to buy fuses instead of for them to design their product correctly. I'm kind of disappointed in that. But it makes this job a lot easier. And I think as I go through why it makes it easier, you'll understand. So I have another inverter just like this. I have not yet disassembled that one. It's over here. I can use this to try to parallel. But here's the general plan, and I want to go over that with you. So the way the inverter works is first you take 12 volts DC, bring it in here, store it in these caps, and these chop that 12 volts DC into 12 volts AC. You send it through the transformer, it gets rectified and stored in this capacitor. Now, because it goes through these diodes, you can't have any backfeeding. All I have to do is take the output stage of this inverter, it's huge, this inverter, and connect it directly to this capacitor. So if I take the capacitor in this inverter and connect it directly to the capacitor in this inverter, I have now effectively doubled the high voltage DC supply. And I need to in no way connect any of the control circuitry together. It's all independent. Because if one of the voltages is higher than the other one, neither inverter cares. It's rectified through this bridge. It doesn't matter at all. So I can just safely connect both of these capacitors together. And they are both resistance-based circuits. FETs have a higher resistance when they're hot and higher resistance when they're under load. Same with the transformer and everything else in here. So they are resistance-based devices. They'll share current very well as long as they're fairly well matched. And because these are identical inverters, they are well matched. Now after this capacitor is directly connected together, I should be able to get twice the power out of the output stage because they're connected directly together. And if you open up higher output inverters, that's exactly what they do. 5,000 watt inverter might be two 2,000 watt inverters connected together, for example. But the output stage is also important, right? Because you get high voltage DC. Yippee, that does nobody any good. So we have some FETs over here to chop that DC into AC for you and send it out the outlets. And what I'm going to do is only use one of these inverters for the output stage. And that may seem a little unorthodox, but there's a reason for that. I actually looked up the part numbers of these transistors, and they are rated for a pretty good current and a pretty good power dissipation. And I also ran both of these inverters under load, and the input stage got very hot, the output stage stayed cool. So I'm pretty sure I can use the output stage of just one of these inverters, and it will be adequate to output double the current. It's well within the rating of the parts, and then I don't have to worry about tying the control circuitry together and all that nonsense. So I'm just going to take the output caps of both of these, solder them directly together, and then I will just use one of the two inverters for the output stage. And this hopefully will turn into a 800 watt inverter. But let's get to that and see what the results are. Of course, first I have to disassemble my second inverter. And if you think things like this are not a pain, you are incorrect, and you've probably not done it yourself, at least not enough to get annoyed by it. It takes quite a bit of time to disassemble something like this, and it takes some care to get it back together correctly. which is part of the reason why a lot of these inverters fail in the first place. Because the people in China, or wherever China outsources their labor to, do not do a lot of this stuff with care. And when you open these up, you find all sorts of things that are just terrible and wrong, and somebody didn't do it properly because they didn't care. They're just, some person working in an assembly line, 10-hour days, 6 days a week, just to be able to feed their family. And then we here in wealthier countries insult them for what they do and say that, hey, you're not doing a good enough job. Well, yeah, I kind of feel for those people. But in any case, it's unfortunate that products are made with such poor quality care. I'm not insulting Schumacher at all for these inverters. They seem above average, really, in quality, but it takes a lot of hand labor to assemble or disassemble one of these. You take out 4 screws on each end panel. You take out 4 on the bottom to get the bottom stamped steel plate off. So you get all that disassembled, and now you are left with this. The circuit board's still stuck in. So here we have a bunch of heat sinks over here, held on by a screw, and this thing. They're really a pain to put back together, believe me. Over here we have some more FETs that are clamped to this heatsink, and this heatsink is clamped to here. You remove all of those, but you're not done yet. You still have to pry each of these FETs off of this anodized aluminum, and then slide the whole thing out and reassemble, which takes far longer than disassembly. Anyway, I'll do that, and we'll take a look at both of these. I have both of these inverters disassembled, laying side by side, and I'm going to do the same thing to both of them. Here's the input cables. They go to this node here and to this node here. Now this one is fairly large. There shouldn't be a problem carrying the current to this node, but this one, all of the current from the input, 50 amps or so, has to go through this tiny little channel over here to this wire, has to go over here, and then it finally connects to this copper port. And really that's a pretty poor design, so I'm going to beef that up and hopefully drop our input voltage drop loss by a little bit. So I'm going to take some solder. This is Eutectic 6337 solder, and beef up this bus bar by a little bit. Now solder is a pretty poor conductor of electricity, to be honest. So it doesn't do a whole lot of good to add solder to something. Really, they should have designed it properly to start with, but since they didn't, there's not a lot of other options, is there? So we're just going to add some solder to this, and it will help somewhat to lower the resistance across this connection, and it should give us a little bit more output capability. Now, a lot of cheaper inverters employ this method of increasing the output capacity. They just glob solder onto places where there should have been more copper and call it good. I don't like doing that, but that's what I'm going to do in this case. So I'll do it to this inverter here and also to the other inverter, and hopefully that will help slightly in increasing the output capability. Now I could also replace these input transistors, but really the point of this video is to see what you can do with what you have without making any major changes. All you need is a soldering iron and some solder. Now to connect these two inverters together, I have wire. Now the output stage is pretty low current, so I don't have to worry a lot about current. At the most they'll carry 8 amps, so this is wire. Yeah, that's pretty much all you have to worry about. So I'm going to connect the negative to the negative and the positive to the positive. Pretty basic stuff, but I should just be able to connect these output capacitors over here directly together with this wire, and then the input stage should be improved. Be able to handle about twice as much current, so I will go ahead and do that. And there they are, connected directly together. So the high voltage output, which is 150 volts or so, is tied directly together. And both of these inverters are sitting here next to each other. The power switch is on both of them. And they are connected directly together with these alligator clips. Over here we have the input positive and negative. They run over to the battery. Over here, this is just a dinky little battery. I'm using this because this battery effectively acts as a current limiter. And I'm running both of the inverters through this single clamp meter. That way I can see if there is excessive current draw with either of these inverters. So right now it's at 0 amps. Both the switches are on. As soon as I make contact here, the inverters will try to start up. And let's see what the input current is when I do that. And you can see that the input current is very, very low. 0.2 amps or so. Now each of these inverters separately probably draws 0.1 amps or so from the battery under no load. So they are operating perfectly normally. And nothing, I just disconnected the power, nothing's getting even the least bit warm on either side, input or output on either one. So it looks like that this method here has worked in connecting both of them in parallel. Now I'm going to reassemble them in their cases because these FETs need heat sinking on both sides of both inverters. Without that they'll just explode right away and smoke, and that won't be good. So I'm going to reassemble these, and then we'll take a closer look at what this has done. And here's our new and hopefully improved inverter. Two inverters that I just strapped together with electrical tape. The input side and the output side. You can turn one of them on if you just want a little bit of power, or both if you want a lot of power. Each one that you turn on will consume a little bit, so it gives you the option. You can either connect 400 watts to this outlet and 400 to this outlet for optimum efficiency, or you can connect a 800 watt load to one of the two outlets and get maximum surge performance. Your choice. The bottom plates I left off for both of the inverters. There are two plates here. For both of them I just left it open so that there's good airflow inside. Each one has a fan. Each one blows over a different half of the inverter, so that works out great. And let's see how this thing works, if it works.